Hey guys, here we are again with some more MATH64 progress. From the previous build where it's got the menu system, we've added a bit more to that. I'll just give you a quick tour around it. Because we can, you know. Got one new thing down the bottom there. We'll wait for a second on that. Got this particular particle script loaded. Let's go to the run window. We can check our variables. We haven't run it yet. We can run it. Yeah, nothing interesting happened. But we can also do a disassembly view. And this is one of the particle demos we had the other day. Well, actually, geez, it was months ago now, sorry. Months and months and months have gone by. Christmas has been and gone. Unbelievable. So let's have a go at particles now. It pretty much runs how I expected. When the pixels are in white, they are I think it's version 1 of the demo. And when I hold the mouse button down, we're running in MATH64. Now we're potentially getting a bit of a speed up, which is actually kind of interesting to me. If I release the mouse, I think the speed here is like really pretty much as we've got other stuff going on in the background on the system at the moment. What I was hoping for is not a huge speed up, is that I was hoping that it wouldn't be super slow. I'll go through that in a second. So it can be done, it is doing it, and let's have a look at how it does it. So I've just pulled this particles demo into the ecosystem of this test. Pretty much left the example as it is, wrapped up the main part of the main loop pretty much, put it in a function that I can call from the menu system. So I can jump to the particle demo, and when you hit space, you return back to where the call came from, in this case the menu. So this is the very base, the naive version of the particle demo. In this version we're looking for a script called process particle, which is defined down below. It's loaded into memory and compiled as a script from the source code directly. You lost yet? You probably will be. So, here I've got displaying the script index. We don't need that at all. And we've got two different versions of draw, which is the plotting the particles and plotting their trajectories, etc. We've got the classic version, and we've also got the 64, which is short for MATH64, with the script index being passed in. If we look at the first version, that's the spawning routine. This is as you would remember it, I hope. Very simple. We're running through an array of these, a typed array. We're looking for cells that have a structure in them, which is anything with non-zero. So if this was empty, it would be 0 and would fail and just skip over the internal logic. We grab a pointer to this particle, so we don't have to use the array index anymore. We've got this defined up here, T particle. It's a nice way of shortening those expressions there if you want to, and there is performance benefits in doing this. We're adding the velocity to the current position, storing it in a variable, doing a range check. If it's outside the range, killing it off. Same thing for Y pretty much. Checking if it's on screen, if it's gone below the screen lower limit, kill it. If it's not, we draw it. Moving on, we apply some gravity and then remember its position for next frame, so the cycle continues on. That's how it works in the PB version. If we flip down here to the MATH64 version, got some differences. Yeah, So here we're asking the scripting library for the pointer to the compiled program. If it wasn't successful, it'll return 0, and hopefully it won't crash out. At the moment, it probably will. So if this script didn't compile properly for some reason, then this value might point to a program that's broken. Just heads up there. Now here we're asking for the pointer to the program to a variable status. Now we haven't looked at the actual function code as yet, but there is a variable called status in it. And our main loop has shifted from all of the logic, really, as it was in the previous one, to we are grabbing a pointer to a particle structure, which is a 32-bit group of floats. That's all we have in PB internally, 32-bit floats. Here we're saying copy this structure of floats, 5 of them, the first 5, into the program at wherever the status variable is. Now we should have a look at the actual function itself. This is the function down here, by the way. This is the script function, it's not PB code. The first 5 values are these ones here. We have status, which is a 64-bit float, position and speed. We're copying 5 values because these are vector 2s. They have an X field and a Y field side by side. So status and 2 vectors gives us 5 floats. We don't need to copy anything more than that because the rest of these are internal for internal use only of the script. Heading back to here, so we copy 5 values from our structure in 32-bit into the script memory, we execute the program, and then we copy the result back, copy those 5 values back. So we're copying the data from our side to the script side, running the program, copying from the script side back to our side so we can access these data as normal. Now it's kind of funky with this particular demo, so we need to do clipping in the script side as well as our side. So here I've got a status comparison, checking if the dot is actually on screen or not. If it's not, we do a check to see if we're above the screen height or below, because status is different depending on what kind of clipping there was occurring inside the script. So that's our execution loop, and we could add more stuff to the internal loop, but I'm kind of amazed that this runs about the same speed. It's probably a little bit slower, and I'm amazed for a couple of reasons. We've got a few things in here that are doing searching. When I search for string in here, it does a hash of the string, then searches through the variable table in this program. Technically what we should do is we should find where this pointer, get a pointer to this status variable up here somewhere and do a copy of this memory directly and never have any string operations in it at all. In other words, we're doing, if there's 90,000 particles on screen, we're doing 180,000 string lookups. Mental. So I think there's a bit of performance laying on the table there, and most importantly, in the script itself, we've got a bunch of ugly stuff in it. Here I've got a pair of vectors to do with the clipping to the viewport. So clip top represents a vector at 0, 0 pretty much. So we just leave it as is because it will be 0 by default. Clip bottom, I'm having to set these values in the script every time it runs. Now I shouldn't have to. It just turns out that there's a problem with comparisons at the moment. I think there's something a bit wonky going on with literals inside the scripting language itself, and it's not picking them up. When we try and do a vector operation with a literal, we're getting some wonky stuff. So I'm having to set these values here directly in this structure, in the vector 2, and then later on I'm doing comparisons against these variables. In reality, I don't need that. I could just get rid of these here, but if I do that, it won't work. I'll get rid of this one here, Which one's that one? Clip X, where we're clipping the X. So bottom X, 799. I'll show you what happens. Do a quick save, we'll run it again. Go back to particles. So this is just normal inbuilt PB codes driving this version. Hold the mouse button down and we get no response. The reason why that's happening is the comparison's not working correctly. It doesn't know what to do when it sees a vector field with a literal. It's confused. So we need to flesh that support out a bit better. I thought it was built in, but obviously it's not. Things happen, man. Press space to go out of it, get back to here. If we look at go to the run tab and look at the code, there's nothing from the disassembled code that's really that glaringly obvious as what's going on. If we can get rid of those, we can get rid of the two moves at the top here. Come down here. These two moves here wouldn't be necessary. This copy wouldn't be necessary, so that's at least 3 instructions from the 64-bit side that we can get rid of. And these separated comparisons are probably not necessary as well. So I think what we'll do, we'll add like a range comparison as well, because we do have range comparisons in PB. Add some of those kind of general purpose math functions for doing that kind of brute force clipping, and that would get us to a point where I think we're comfortably faster than the internal code without much effort. I mean, it's messy, granted, you know. Yeah. Let's restore that to where it was before. It took me a little while to work out what's going on with this because I ran into this problem yesterday pretty much. I was putting this together and it was crashing, doing some weird stuff, and I couldn't work out why it was crashing. It just turned out that those comparisons weren't working properly. Bit of a bummer. So in this code here, we wouldn't need these variables here at all. These assignments up the front here. And if we have a range check, we could make this in here. What we also need actually is a way of aborting the script early. At the moment, it'll keep running through the script regardless. So even though if y is greater than the bottom of the screen, or its clipping range of the screen, it will keep running the rest of these expressions. There's no way to get, I can't just go end, which would be nice. So I have to add that to it. This is the cool things about when we do these kind of weird tests, you know, you run into just everyday, you know, problems like this. Things that you should have, but they're just not built in. They're not done. Obviously, if we had more stuff done in the script side, we're going to benefit better. I'm not quite sure how we could do. Like at the moment, we're feeding it one particle at a time, doing a particle. Now we could do pairs of particles. I've mentioned this before. That would probably horrify people how that would be done. But I will say that because this is script and you can modify the script at compile time, if these were literals, these clipping values in here, right, which they can be literals, if you change the size of the screen at some point and you need to reset those things there, you just recompile the script and replace those literal values with something else. So what you might do is not bother pre-compiling this thing, is you might just load this in as a chunk of text and do, where's that text? Let's say you've got, I'll put a comment beside that. Let's say here is this is the, what do I call that? Clipping. Or say, I'll call it just called screen width. You know. I know it's kind of hard to imagine how this would work, but you would load this script in as a chunk of text, do a straight replace on this, and replace it with whatever width that you require. And that would just work as normal. It's nothing. Yeah. If you want to do this stuff in parallel, you can have this structure here. I won't make this work, but we have, you know, status 1 for these ones here. Sorry, status 2, speed 2. Now, inside the script, you could have this same logic from down, where are we? Down here somewhere. Repeat it. Just copy and paste it, pretty much. You have to replace all of these variables that we just changed the names of, like status 1 becomes status 1, status 2 becomes status 2. You're kind of making an array of these things. So in our driving routine here, we read 2 particles in and copy the particles from status 1 and then into status. Mock that up very quickly. You see what you get what I mean. And we need to read a second particle there, but you kind of get what's going on. And what that would do is that reduces the number of execution calls. We've got half as many execution calls over the total number of particles processed. We're doing less loops through this particle here because we're treating particles as groups of pairs. Wow. I know it's gobbledygook to people, I'm sorry about that. I hope you're sort of following what I'm talking about. Because the whole goal is to not, if you want to do high performance particles, for example, you really shouldn't have one-on-one management. Best way to do it is actually to do batches. So you could have a script that runs particles that move right, particles that move left, and then you only ever need to have comparisons again one part of the viewport. If the particle's never moving up and it starts on screen, why would you ever compare it against the top part of the viewport? It's impossible for it to leave the screen like that. So its code here should be reflected in that. It's a bit more fiddling around, but obviously if you assert yourself, you could make some wacky stuff happen. I do mean wacky. All right, I think that's probably all we wanted to look at here. A bit of an overview of what's happening. The functions in here are starting to build up a bit more and becoming a bit more robust. We have uncovered that we do need a way of copying 32-bit floats to 64-bit floats, and possibly a way of doing an integer method of the same idea. So you might be able to have something like, I'll just jump out of this for a second. You know, let's say you've got like a function to, I don't know, copy 32-bit floats as 64-bit or something. So you have your source pointer, a destination pointer, so this is where, in this case, if you're copying from a type, it would be the pointer to the type. This is the location of the variable inside memory. You might have the number of bytes you want to copy, number of floats, or number of we'll have count. But we might have a type list at the end here. Data type mask, let's call it. The mask would be used as like an on or off switch for if it's an integer or a float. That would let you copy patterns of memory across. So you could have some flags that are integer, some flags that are float. Copy them across. It would recast them all as 64-bit floats internally, that's a massive tongue twister for me. And once you're done, copy them back with the same mask. So if you want to copy, say, 5 values, let's say, we might have this. We have 5 of them, but our data is specified like this. If we, hang on, we have a bit mask here, and we use the high bit or a low 5. Yeah, 5. We know how many bits we're going to copy. It's this 5 here. So let's say if we have the first bit set to 1, that means copy it as a float. We might have a float and then an integer and a float. You know, it's not a pretty solution. It means we can only have runs of 32 floats or mixtures of these things in one hit. But it solves an ugly problem. You know, otherwise you have to specify the pattern of memory you're copying from to copy it across, which is way beyond the scope of what we're trying to do. Well, I think so anyway. Maybe you don't. I mean, who knows? You know, so if you wanted to copy this one here, that was just all floats. Yeah. Let's say it was this, and they were all floats, so just be like that. If you want to copy a version that was an integer, float, it would be like that. That kind of thing. So that approach could work pretty well. I don't know, you know, I'm just riffing at the moment. Anyway, we'll put this together, put the new files up on the forum for you, and you can mess around with it and scream and yell at it all you want. Anyway, thanks for watching. Hopefully you picked up something about this process. Hopefully it's not as mysterious as what it was before. It pretty much is at the moment. We've got some bugs in there. We've got a squash. We're getting closer to something kind of cool and fun to mess around with. Till next time, see ya, bye.